Hey guys, Mr. Butts here. I want to talk about another application that we can use calculus for. This is actually one we've talked about previously with derivatives, and now we're going to talk about how we can apply integrals to it. So when we're talking about motion problems, we look at things like position, velocity, and acceleration, and those are related to each other using calculus. So if you remember, the velocity of an object is the derivative of that object's position, and the acceleration of the object is the derivative of that object's velocity. Well, also remember that integrals are closely tied to derivatives because of that fundamental theorem of calculus. So we can use integrals to work with these things also. So let's jump into it here. And a quick refresher. Velocity and speed are two words that are often used interchangeably in common language, but they mean very specific things in physics and in calculus. So we want to make sure that we know the difference between them. Speed, remember, just measures how fast something is moving. Velocity not only tells us how fast it's moving, but also in what direction. So when we're talking about linear motion, which is going to be a lot of the physics problems we're going to do, we're going to be looking at either a positive direction or a negative direction, so forward or backwards. Speed is more specifically the absolute value of velocity. So if an object is moving 10 meters per second forward or 10 meters per second backwards, the velocities are opposites, but the speeds are going to be the same. Also, another note on speed and velocity, the units that we're going to use are going to be distance divided by time because speed and velocity both represent a change in position with respect to time, and position is measured with distance units, and time is measured, obviously, with time units. So if we look at another idea here, displacement versus distance traveled. These are two very similar topics, very similar terms, but they also mean very different things depending on the context. So let's say we have a an object moving along the x-axis. So it starts at some point and it moves along. Its displacement and its distance traveled are just the distance between those two. So if we can measure this right here, it's that distance. So the coordinates here, let's say this is x1 and this is x2. The distance it's traveled would be x2 minus x1. So if it's at, say, coordinate 9 here and at coordinate 2 here, the distance it's traveled is 7. However, if the object moves to the right for some period of time, and then it moves to the left for some period of time, now the distance it's traveled is going to be the distance that it traveled from x1 to x2. So it would be x2 minus x1 plus the distance that it traveled from x2 to x3, which would be x2 minus x3. So the total distance traveled would be those two added together. Notice that distance traveled doesn't take into account whether we're moving to the right or to the left. However, displacement is just the distance from where an object starts to where it ends. So that's a very similar idea, but also a very different idea. So it's really important that we understand the difference between displacement and distance traveled, because if an object is changing directions, its distance traveled is always increasing, where its displacement might be increasing or decreasing depending on the direction it's going. In this case, the object's displacement is actually going to be x3 minus x1, which ends up being a negative number because the object has ended up moving to the left overall. So to measure displacement, we are going to essentially take the x value where the object ends minus the x value where the object begins, and that gives us a formula for displacement. Well, this right here, this difference is a difference that we can get through a particular integral. Specifically, that's the difference that we get with this integral. So in order to get displacement in a motion problem, we can simply take the definite integral of a velocity. If you remember, to evaluate a definite integral, we take an antiderivative, and since velocity is the derivative of position, the antiderivative of velocity is the position, and we evaluate it from the lower limit to the upper limit, and we get that. So displacement is simply the definite integral of the velocity over the time interval. And this definite integral then will tell us how far the object has moved to the right or to the left over some time period. Distance traveled, on the other hand, since it's always increasing, is actually the definite integral of the speed. So rather than taking the integral of velocity, we take the definite integral of speed, and that tells us how far an object has traveled over some time interval. So say I start, let's say I'm standing right here, and I run a mile that way, and I run a mile this way. My total distance traveled given by this right here is going to be 2 miles, where my displacement given by this integral right here is going to be 0. Obviously, those are two very different things, and if I'm running 2 miles, I want to get credit for that. However, since I'm ending up where I started, my displacement is 0. So these two formulas are very important. We will use displacement a little more often than distance traveled, but when you see a problem that involves distance traveled, it's important that we know that we're using speed rather than velocity for our integrand. Another useful application of this is we can take this displacement formula, knowing that the displacement is given by the definite integral of the velocity, and it's also the difference between the x position where we end and the x position where we begin, and we can manipulate that formula in a way that gives us this formula right here. And so we can use this to find the position of something at any given time, knowing an initial position and then integrating velocity from the initial time to the final time. This formula right here is a specific version of a generalized net formula or net change formula that we're going to use very often with applications of rate of change problems. Okay, so this is, like I said, a specific example where we can use a net change formula where we are taking a starting condition, an initial condition, and adding on the change. So if we integrate velocity, that gives us displacement, which is how far the object has moved or the change in its position. So if we take the initial position plus its change, then we get a final position. This is also a very important formula. In fact, the general net change formula is probably the most important formula we're going to use all year. One other thing, we can apply the same idea. Since position is the derivative of velocity, we got these formulas here. Well, since acceleration is the derivative of velocity, we can take that another step, and we can find a change in velocity by integrating acceleration. And so if we want to know a velocity at any given time, knowing an initial velocity and having an acceleration formula, we can integrate acceleration to get a change in velocity and use that net change formula to find a change in velocity and ultimately a final velocity. So again, that net change formula, very useful in these motion problems. And we need to understand the relationship then between position, velocity, and acceleration in order to apply that.